Okay, welcome to this tutorial. My name is Brian Madena and my colleague is Emmanuel Wambua. So today we are going to introduce this concept of interpolation. So basically, interpolation is the process of estimating values of a function f of x for arguments between data points x0, x1, x2, all the way to xn. So what you're saying is that you're estimating values. Suppose you're given values, a set of values. Estimating values between these two or between these two, that is what we call interpolation. Now, the values of the function are known to be f of x0, f of x1, and f of x2, all the way to f of xn. We can simply denote f of x0 as f0, okay? F of x1 as f1, f of x2 as f2, f of xn as fn. And these ones are usually given on a table as follows. So this will be our x0, this will be our x1, this will be our x2, this goes all the way to xn. This will be our f0, this will be our f1, goes all the way to fn. Now, getting the values in between these data points, okay, in between here, that is what we call interpolation. Now, interpolation is important to us, so let us look at the uses of interpolation. Uses of interpolation: reconstructing functions if not explicitly given. If not explicitly given. Now, in this example, in this table up here, you are not given a function, but a set of data points. However, we would like, for example, to come up with a function that will govern this set of data. So we can reconstruct that function using this technique of interpolation. Then, another use of interpolation is replacing a function f of x by an interpolating polynomial p of x. And so, what is this interpolating polynomial that you are calling p of x? It is simply a polynomial that its value or its certain order derivatives coincide with those of a function f of x at one or more tabular points. Say f of x0 is approximately equal to p of x0. Similarly, f of x1 will be approximately equal to p of x1. The derivative of f of x0 will be approximately equal to the derivative of p of x0. Now, this p of x0 is what we call the interpolating polynomial. Then, we come to the techniques that we use for interpolation. So, under the techniques that we use for interpolation, the first technique is interpolation based on Taylor series. Basically, what we do in this form of interpolation, as we shall see in the next examples, is that given a function, we get its Taylor series equivalent, and of course the Taylor series of any function is usually going to be a function of x. So therefore, that function of x that you're going to get after representing the function in its Taylor series equivalent is what you're going to call an interpolating polynomial. Because a function with its Taylor series are approximately equal. The next technique is the Lagrange interpolation technique. The Lagrange interpolation technique uses various definitions and Lagrange formulas and Lagrange fundamentals or coefficients so that we can come up with an interpolating polynomial. In this case, the interpolating polynomial takes the form of Pn of x is equals to L naught, F naught, L1, F1 plus L2, F2 all the way to Ln, Fn. Okay? Where L0, L1, L2 to Ln are what we call the Lagrange fundamentals or Lagrange coefficient. Lagrange fundamentals or Lagrange coefficient. So, this technique, basically, we shall come with formulas on how we are going to obtain the Lagrange fundamentals. Generally, we can say the Lagrange polynomial Pn of x is given as the summation from I is equals to 0 to n of Li of x, f of xi. Okay? So, this simply means this is just a condensed form of this. So, the condensed form of this is this. So, do not get frightened if you see me giving it the Lagrange interpolating polynomial as this. As for the Lagrange coefficient or the Lagrange fundamental, I is given as j is equals to 0 to n x minus xj over xi minus xj. Okay, these ones will be more meaningful when we do examples or when you look the specific videos under these techniques of interpolation. The next interpolation method will be the Newton divided difference technique. As the name suggests, we are going to have differences, then those differences we are going to get a division by a certain factor to those differences. And the Newton divided difference technique, which I can simply just say NDDT, Newton divided difference technique, has a general form of a polynomial Pn of x given as b0 plus b1 x minus x0 plus b2 x minus x0 x minus x1, and this continues, okay, with the same pattern. Then we come to the Gregory-Newton forward difference technique. In this case, we do not use divided differences. We only use differences, okay? Difference, that's subtraction. Therefore, what this one basically means, we shall see how and why it's called forward when we look at this technique in detail. And this Gregory-Newton difference technique, basically, we are going to use finite differential operators. Finite under the topic of finite differences. That is, they have the forward operator, finite operator, and you have the backward operators. Forward operator is denoted as forward differences, and backward differences will be noted as with this symbol. So this is for backward, and this is for forward differences. So the general formula of the Gregory-Newton forward difference technique, which I can just say G and Gregory-Newton forward difference technique, is P of x0 plus sh is given as f of x0 plus s. Then we are going to have this operator, okay, of x0 I mean, sorry about that, over 1 factorial plus s minus 1, then you have that squared, okay, f of x0 over 2 factorial plus s into s minus 1, s minus 2 into that f of x naught over 3 factorial. And the process still continues. We shall derive these formulas when we go to the specific videos that deal with these specific techniques. The other technique we are going to look is the Gregory-Newton backward difference technique. This is we can simply say is GND B dt. This one basically it's more so like the forward difference technique. However, instead of using the first value, that is x naught, we begin with the last value, that is xn. Therefore, wherever you're going to have x naught, we put xn. So this will be p of xn plus sh will be equal to f of xn plus s into, now you cannot denote this way, so we are going to use the backward differential operator, that is that way, f of xn over 1 factorial plus s, instead of minus we are going to have a plus, so s plus 1. We'll see how this comes about. Then don't forget the symbol that is inverted, s squared f of xn, not x naught, over 2 factorial plus s into s plus 1 into s plus 2, okay, the symbol is inverted, okay, cubed, f of xn over 3 factorial, and this continues, okay. So basically these are the techniques that we'll be using. We have some few things that we can note, that these techniques that we have, the interpolation based on Taylor series and the Lagrange interpolation technique and the Newton divided difference technique, they can be used to estimate values or for interpolation for set of values which are unevenly spaced. So we can just say this is unevenly spaced. Unevenly spaced. Unevenly spaced. And the Gregory-Newton forward and backward is usually used for evenly spaced set of values. Evenly spaced. What I mean with evenly spaced is that suppose x naught is 1, x2 will be 2, x3 will be 3, and x4 will be 4. So if you look at this step size, the difference is 1, 1, 1. So we say that this one is evenly spaced. Unevenly spaced, you can see for unevenly spaced, this can be any number instead of 1. Any number instead of 1. Another thing, Gregory-Newton forward difference technique is used to, the forward difference technique is used to interpolate for values that are close to the beginning. And that is why we are having x naught as our point of reference. However, Gregory-Newton backward difference technique is used for interpolation of values that are close to the end. And that's why we have xn, which xn is our last value. We shall go through all these techniques and we shall see how we can use all these techniques for interpolation. So, please, with that, I'd like to end this tutorial today. Just know this is just an introduction and an overview of interpolation. So please do not forget to subscribe to our channel and hit on the like button, and therefore, thank you.